So we're going to continue talking about properties of the ordinary least squares estimates of our regression parameters. If you remember, at the end of the last class, we derived a closed form expression to estimate the regression parameters using ordinary least squares. So if x is a matrix containing a column of 1s for our intercept and the other regressors side by side along with that, and y is our vector of responses, then the ordinary least squares estimate of the regression parameters contained in the vector beta is x transpose x inverse x transpose y. And this is a nice closed form expression, and as long as x has full rank, so we don't have any linear dependency in the columns of x, then this is going to work just fine for estimating our regression parameters. And so what we want to do is we want to look at some of the properties of the ordinary least squares estimates of beta, and we'll have some lemmas along the way that we'll need to prove. And so that's what we're going to do as we start here. So the first thing we want to do is show that the identity matrix minus the hat matrix is symmetric and idempotent. And in case you don't remember what the hat matrix is, we defined it earlier in the chapter. The hat matrix or projection matrix is a matrix that projects the response vector onto the space spanned by the matrix related to the regressors, and it's defined by x times x transpose x inverse times x transpose. And so this is the matrix, the hat matrix. We're talking about H, and it will be defined consistently throughout the semester. And we want to show that I minus H is symmetric and idempotent. So for those of you who haven't had a linear algebra course recently, let me remind you what symmetric and idempotent mean. So let's assume that A is a square n by n matrix, and A is symmetric if A is equal to A transpose. Okay, so there's an aspect of symmetry there. And then idempotent, which I always think is a really cool describing word, means that A times A equals A. And so we want to show that I minus H is symmetric and is idempotent. So what I want you guys to do is I want you guys to pause this lecture, and then after you guys have a chance to try to work through this on your own, then we will show that I minus H is symmetric and idempotent to make sure that we are all on the right track. Okay, well hopefully that went well for you guys. We will just start right away with our results here. So I'm going to write what H is, just so we have it fixed in our minds. So H is x transpose x times x transpose x inverse times x transpose. And so we need to show that I minus H equals I minus H transpose. And so let's actually just start here. So I minus H transpose is going to be I transpose minus H transpose. And using substitution, so erase that so we don't get confused there. So I minus H transpose is I transpose minus H transpose, but the identity matrix is symmetric, so we just get I, and then H transpose is going to be x times x transpose x inverse x transpose, and then the whole expression transpose. And you may remember that when you were taking the transpose of a product of matrices, you basically have to reverse the order of the matrices that you're taking the transpose of, and then you transpose each individual matrix. And so what that means is that we get I minus, and then x transpose transpose times x transpose x inverse transpose times x transpose. And the transpose of a transpose is the matrix itself, so we get I minus x. And inverse matrices are symmetric, so that means that we must get x transpose x inverse, and then we're left with x transpose. But this is H. So we get I minus H. But we start off with I minus H transpose. So therefore, I minus H is symmetric. So we've shown the symmetry aspect of this problem. And now we need to show that is idempotent. So we need to show that I minus H times I minus H equals I minus H. That's what we want to show. So the first thing I want to do actually is I'm going to show that H is idempotent. So H times H is X transpose X, X times X transpose X inverse times X transpose. We multiply that by the same thing, X times X transpose X inverse times X transpose. And what we notice is that we have an X transpose X right there. We have an X transpose X inverse. So this becomes X times the identity matrix times X transpose X inverse times X transpose, which simplifies to X times X transpose X inverse X transpose, which is H by substitution or by definition. So we've shown that H is in fact idempotent, and this is going to be helpful to us. So I minus H times I minus H. Okay, so I multiply I and I, so I get the identity. I'm going to get a minus H plus H times H. And this becomes I minus 2H plus H times H. But since we've shown that H times H is equal to H, by substitution we get I minus 2H plus H. We have minus 2H plus H, so we have I minus H. And so we've shown that I minus H times I minus H equals I minus H, which means that, therefore, I minus H is idempotent. Okay, so we've shown what we needed to show, and hopefully that you are successful in doing the same thing. So now we want to show another identity. So we're going to look at the residual sums of squares, or RSS. And the residual sums of squares is just the sum of the squared residuals. And in matrix form, that's just epsilon hat transpose epsilon hat. And we want to show that epsilon hat transpose epsilon hat is equal to y transpose I minus h y. So we're going to have to use some of the identities related to epsilon hat and some of the things that we just learned to show this. So just to remind you, we said that epsilon hat could be written as I minus h times y, and we're going to use that in our proof here. So we're looking at epsilon hat, which is I minus h times y, and we are going to be calculating the residual sums of squares, which is epsilon hat transpose epsilon hat, which by substitution is going to be I minus h times y transpose times I minus h times y. And so simplifying this transpose on this left-hand side, we get y transpose times I minus h transpose times I minus hy. But we have just proven that I minus h is symmetric, which means that I minus h transpose is just I minus h. And we have also just shown that I minus h is idempotent, which means that I minus h times I minus h is just I minus h. So we get y transpose I minus h times y, which is exactly what we wanted to show. And now we'll move on to some more interesting properties of the ordinary least squares estimate of beta hat. So one of the main reasons that people really like the ordinary least squares estimator of beta is that it is an unbiased estimator for beta. And even more importantly, it also has the minimum variance among all unbiased estimators, assuming that the errors are uncorrelated with each other and have constant variance, which the mathematical way of writing that is that the variance of epsilon equals sigma squared times the identity matrix. So that is the same as the errors are uncorrelated, identically distributed, and have mean zero and variance sigma squared. So we will make use of these properties to show that beta hat is an unbiased estimator of beta. So what I want you guys to do actually is I want you guys to pause this. I want you to see if you can't work this out on your own. And so just to give you a little bit of a hint, a little bit of direction here, to show that beta hat is unbiased for beta, we want to show that the expected value of beta hat equals beta. And so you're going to substitute in the formula or expression we have for beta hat, take the expected value, and try to show that that is equal to beta. So why don't you take some time, 5 minutes, 10 minutes, maybe even 15 minutes, and see if you can't work out the solution on your own, and we'll come back together in a few minutes and look at the solution as a class. Okay, well, hopefully you were successful, or at least made some really good progress as you were trying to show that beta hat was an unbiased estimator of beta. So this is a complicated thing to show. I don't want to trivialize it and make it seem like it's easy. It's one of those things where you definitely need to know where to start if you're going to be successful. And just to make things as clear as possible here, what I want to do is I'm actually going to start off by finding the expected value of y, because we're going to use that in our proof here. So the expected value of y. So y, you may remember, y is equal to x beta plus epsilon. So we have that defined earlier in our notes, in the matrix notation. Okay, right here. So y is equal to x beta plus epsilon. And so by substitution, we're going to replace y with x beta plus epsilon. So we're trying to find the expected value of x beta plus epsilon. And x is going to be a matrix of constants. Beta is a matrix of constants. Whereas epsilon is actually a vector of random variables. It's a random vector. But what that means, actually, we don't even need this yet, but the expected value of a sum is the sum of the expected values. So this is the expected value of x beta plus the expected value of epsilon. So that's by the linearity of the expected value operator. But x and beta are both constants. And we have talked about in our review section that the expected value of a constant or a matrix of constants is just those constants. So the expected value of x beta is just x beta. And the expected value of epsilon, well, this is the expected value of a random variable. But hopefully you recall that we have assumed that the expected value of the errors is 0. This is something that we've been assuming ever since we started this chapter. So go back and find where we talked about this. Here we go. You can always assume the expected value of the errors is equal to 0. Since, if this is not the case, we can always absorb it into the structural part of the model so that the errors do have 0 expectation. So we can always assume that the errors are mean 0. And so the expected value of epsilon is just 0 there. And so the expected value of y is just x beta. Okay, so that's going to be helpful as we are working out the result for the expected value of beta hat. So the expected value of beta hat is going to be the expected value of x transpose x inverse times x transpose y. And this part right here is constant. And we know that we can pull constant matrices out of the expectation. So this becomes x transpose x inverse x transpose times the expected value of y. But we've actually just calculated the expected value of y, haven't we? And so, so just to be clear here, so this is because x transpose x inverse x transpose is constant. And now we can substitute in for the expected value of y based on what we have previously done. So we get x transpose x inverse x transpose times x beta by substitution. But now you can see that, sorry, I'm not sure what that happened. we go. So now we can see that we have x transpose x inverse, and then we also have an x transpose x inverse. So those cancel each other out. We get the identity, and identity matrix times the beta vector is going to be beta. And so we have in fact shown that the expected value of beta hat is equal to beta. So we have shown that beta hat is an unbiased estimator of beta. So we have completed our task. And another important quantity that we need to calculate related to the properties of the ordinary least squares estimator is the variance of the estimator. And so what we have here, so I'm just going to tell you the answer first of all, and then we're going to show that this is in fact the case. So we're going to assume that the errors are in fact uncorrelated, identically distributed, with mean 0 and variance sigma squared, which in matrix notation means that the variance of epsilon is sigma squared times the identity. Okay, we saw that way back here. Okay. And so we're going to make that assumption, and under that assumption we want to show that the variance of beta hat, the variance of our least squares estimator, is sigma squared times x transpose x inverse. So once again, why don't you pause this for a few minutes, try to use the properties that you learned in the review section of the course to derive the variance or covariance matrix of beta hat. So why don't you pause this, take a few minutes, and then we'll come back and look at the solution as a class. Well, I hope that exercise went well. We are now going to look at the solution together just to make sure that we are all on the same place. So we are looking at the variance of beta hat. And you may recall that the variance of a constant matrix A multiplied by a y was A times the variance of y times A transpose. And the reason why I remind you of that is because we're going to use that in our proof here. So the variance of beta hat by substitution is the variance of x transpose x inverse x transpose y. And this right here is a set of constants. Because of that, we can pull the constant out front and then also pull it out on the back side. So we're going to get x transpose x inverse x transpose times the variance of y. And then the transpose of this is going to be x times x transpose x inverse, which I'll leave you to verify. So we have this variance of y right here. We're going to need to figure that out. We know that the variance of epsilon is sigma squared times the identity. And can that help us? So the variance of y is the variance of x beta plus epsilon, right? So we have defined that before. We actually used that way up here when we first started this. Actually, maybe, there we go. Right, so we use this up here, and we're going to use that again. So the variance of y is the variance of x beta plus epsilon. And these are constants. Okay, this is random. But if you look in our review notes, the variance of a constant plus a random vector is just the variance of the random vector. The constant doesn't increase the spread or the variability of our random variable, it just shifts it around. So this is just the variance of epsilon, which we have already said is sigma squared times the identity matrix. Okay, so that's going to be helpful to us. So now we can use that, we can substitute that back in on this left-hand side of our equations here. So x transpose x inverse, x transpose times sigma squared times the identity matrix times x transpose x inverse. So now I can simplify this. I'm going to pull this constant sigma squared out front. The identity matrix doesn't really do a whole lot. So I get x transpose x inverse times x transpose x times x transpose x inverse. Well, I see an x transpose x here, and I see an x transpose x inverse here. So those will cancel each other out and leave me with the identity. And so I get sigma squared times x transpose x inverse times the identity, which is just sigma squared times x transpose x inverse. And so we have derived the covariance matrix of beta hat. So you can see that it's just this scaling constant, and then it depends on our matrix X, our matrix of regressors. So it's important to derive the covariance matrix of beta hat because that is going to allow us to obtain the standard errors of our estimates. So we have derived the covariance matrix of beta hat. Of course, you probably already realized this, but sigma squared is an unknown constant. So we can't actually compute this in practice. So what we have to do is we actually have to estimate sigma squared and then use that to estimate the variance of beta hat. And we're not going to prove the next result, but in fact, if you take the residual sums of squares and then you divide it by n minus p, where n is the number of observations and p is the number of regression parameters in our model, then that will be an unbiased estimator of sigma squared. And so to estimate the standard error for each regression coefficient, we take the appropriate diagonal element of x transpose x inverse, we take the square root, and then we multiply by sigma hat. And you may notice here that I have I minus 1 over here and I over here. That's actually not a typo. You may recall that we start to index our regression coefficients at 0. The intercept is beta naught. And so if we're trying to find the standard error of beta naught hat, for example, that's going to be in the first position of the covariance, or of the x transpose x inverse. So this is not a typo right here. You just have to offset the regression parameter you're interested in knowing about with the next element of the covariance matrix, because the regression parameters start counting from 0, whereas these elements we start counting from 1. So that's just kind of like a little math thing that you have to be aware of. But in practice, we'll compute this using R, so hopefully that won't confuse you or be a problem when it comes to doing actual computations.